Okay, hi everybody. We're back to continue our talk about the cardiovascular system and the blood vessels. And in part one, we looked at the larger blood vessels, the arteries, and how they affect blood pressure and blood flow, right? So really those larger arteries are where we adjust the overall pressure in our bodies. But now we're going to look at the smaller arteries, the ones that um, attach to our capillaries and bring blood to our capillaries, which are supplying our different organs and things. And these are called the arterioles. So arterioles are where we adjust the flow to the specific organs. This can also help regulate arterial blood pressure as well. Okay, but mostly what we're doing here is we're going to vary the amount of blood that can go to each of the different organs. So recall from the first lecture, you saw that distribution, that tree of different percentages of blood going to different organs. And so we can also increase or decrease that as needed, as the body is needed. And we've talked about some of this already. We talked about how in a sympathetic state, you want to increase blood flow to your skeletal muscles. And so what we're going to discuss now tells us how we can do that. Okay, so the arterioles are called the resistance vessels because these are the ones where we can really adjust the radius independently of the other of the rest of the cardiovascular system. Independently meaning just to that a particular organ that we're interested in. Okay, and so there we go. So you can see this here. So here's a micrograph picture of our arterioles. They are wrapped in smooth muscle. And so it's this smooth muscle that can constrict. It can contract. When it contracts, it causes vasoconstriction. And that reduces the radius of the arteriole itself, which is going to increase resistance, which is going to decrease blood flow. Right? That's vasoconstriction. When our smooth muscles in a particular area of an arteriole relaxes, that causes vasodilation. Okay, that increases the diameter, which then increases blood flow. Okay, so there's less resistance when we increase the diameter, so we increase blood flow. Alrighty, so how do we control that? How do we control whether we vasoconstrict or vasodilate, and also in a particular area of the arteriole? Okay, well, it's controlled both intrinsically and extrinsically, and we have a lot of intrinsic controls. Okay. Oh, here is just a nice picture, just to help some of you understand, maybe this picture helps, how arterioles are actually controlling blood flow. So the valve here would be the symbol of an arteriole. So at this point being that the valve is completely open, meaning our arteriole is dilated, so blood flows through easily. Here, the valve is closing a little, so our arteriole is partially dilated, so blood flow is impeded. And in this one, we've completely shut off the valve, so the arteriole is completely shutting off blood flow to a particular area of the body. Okay, mostly we do this moderate resistance. Okay, so how does this happen? Well, intrinsically, how we control our arterioles has to do with the chemicals that are either building up or decreasing in that localized area where the organ is doing work. So what chemicals? Well, again, we're talking about things like oxygen and CO2, things that our tissues, they're using oxygen, right, when they're doing work. And so that is a kind of a signal to the arteriole whether an organ is doing a lot of work or a little bit of work. So if it's doing a lot of work, it's using a lot of oxygen. So the interstitial fluids in that area where the arterioles are bringing blood to those capillaries, it's going to start to become decreased in oxygen because the organ is using it. And so we're going to see that that is going to influence the diameter. Or as an organ is doing work, remember that during cellular respiration, that we release a lot of CO2. So CO2 can be a signal, okay? These are called metabolic control mechanisms, okay? So the metabolites, remember that the chemical reactions that our cells are doing, all of those chemical reactions we refer to as metabolism. So the chemicals that are getting used or produced because of metabolism then is an indicator to the arterioles, and then the arterioles can match the blood flow to the needs of that localized tissue. So one of the ways it does that is through what I've been talking about as active hyperemia. So the higher the metabolism means the organ is working very hard, means it's going to need a higher blood flow. So the arterioles need to vasodilate. Well, how do the arterioles know how to do that, right? Well, again, as I was just mentioning, if the tissues are working hard, it means they're using oxygen in the cellular respiration process. So the tissues, the interstitial fluid surrounding those tissues are decreasing in oxygen because it's going into the cell and getting used, right? Well, a decrease in oxygen causes the smooth muscle cells associated with the arterioles to relax. So they vasodilate, so that increases blood flow. And remember, the increase in blood flow is bringing more oxygen, right? If cellular respiration is going on, the oxygen is being used. Remember, a waste product of cellular respiration was CO2, carbon dioxide. So that's going to build up in the interstitial fluid where our arterioles are also located. So that chemical now is causing smooth muscle to relax, increasing blood flow. So it sweeps away that blood flow or sweeps away that CO2, okay, and cleaning the waste product out of that area, okay. Metabolism can also cause more acids to occur. Okay, so if something is becoming more acidic, remember the pH is declining. So a pH of like 2, 3, 4, that's acidic. And our tissues don't do well in an acid environment. So increase the blood flow, we carry that away. Okay, and the kidney can then deal with the acids. That's the organ that will get rid of acids. Okay? When cells are doing a lot of work, remember that many times if they're doing electrical potentials are occurring, potassium's going to increase in the interstitial fluid because potassium moves out of cells, remember, and that's where the arterioles are lying. So the smooth muscle respond to that increase in potassium again to vasodilate, sweep that blood out of there to get the potassium out, and that keeps the homeostatic condition so that the tissues can still do work and kick potassium out of their cells as needed. Okay. So that's called active hyperemia. It has to do with the chemicals either being used or created in metabolism. Okay. But another chemical that can be produced is produced by the inner lining of the arteriole. Recall back to anatomy, the very inner tunica intima is lined by simple squamous epithelial tissue, and we call that endothelium in the cardiovascular system. Well, the endothelia can produce paracrine regulators that also promote vasodilation, right? So for example, endothelia can produce nitric oxide. And basically they do that to just set that resting tone of the vessels. At rest, what's the normal diameter we want to occur at our blood vessels? So if it's just gone through a constrictive situation, when things are going back to normal, the endothelial can release nitric oxide and bring those back to normal. Okay, this is what vasodilator drugs are based on. And so if somebody who has a heart condition, sometimes what happens in those heart conditions is that the coronary arteries spasm and they constrict, and that decreases blood flow to their heart, and their heart can't get enough nutrition that it needs and oxygen. So when they feel that tightness, they can take nitroglycerin, and that'll open up those blood vessels and allow the blood flow. This is what the drug Viagra is based on this concept of nitric oxide vasodilating blood vessels. Viagra is a drug that helps men achieve an erection. And the way it does that is by producing nitric oxide, and an erection is produced by the vasodilation of the artery that goes through the penis. Okay, well, originally this drug was being developed for diabetics. Diabetics can get cardiovascular problems as their disease progresses. So originally this was a drug to try to help combat that over time. Well, what happened was the drug went into the clinical trial phase so people can try it. And the men in the clinical trials reported this very odd side effect, but it may have helped their marriages. So instead of saying, oh, the drug was a failure, of course, in America, they find a way to bottle it and market it. And so now we have drugs like Viagra and Cialis and those things. And so it's based on nitric oxide. So if you have a heart problem, that's why there's a warning label on Viagra to not take it, because you can be having too much nitric oxide, which would cause widespread vasodilation and a very dangerous drop in blood pressure. So you have to be careful about these things. Okay. Another chemical produced by the endothelial layer is endothelin-1. This is a vasoconstrictor. This usually happens if there's some sort of tear in the arterial lining, causing blood loss. Then the endothelium will automatically release this endothelin-1, and that'll cause vasoconstriction, slowing the blood flow to that area so you don't lose as much blood. Okay. Histamine, tissues can also release histamine. Usually that happens when there's an organ that's injured or there's an allergic reaction. And so that then causes the arterioles to vasodilate, again, bringing more blood flow, which is causing the inflammatory response. In the case for an injured organ or allergic reactions, you want the immunity cells that the blood are bringing. So if we vasodilate and come along. So that's the swelling that you might experience. Okay, so those are local chemical controls that are signaling the smooth muscle cells in the arterioles, causing an intrinsic control. Okay. And so this picture can show you that as well. We talked about the chemical portions that you see here already. So you can see that maybe there's an increase in oxygen at a tissue, so we're going to constrict, right? The arteriole doesn't need, that's how it knows it doesn't need to bring as much blood flow to the area. Because if there's an increase in oxygen, then the organ isn't working as hard. It's leaving the oxygen out in the interstitial fluid. Right, but here if it decreases, then you're going to get vasodilation, so on and so forth. But now we're going to talk about some of these other ones you see here, the myogenic activity. So physical response, a local physical influence on arteriolar radius. Okay, and again, this causes an intrinsic control. So physically, the organ, you apply heat or cold to the area. Heat is going to warm the area. Remember, our cells can't tolerate too much heat because it denatures enzymes. So blood vessels will vasodilate, sweeping the heat away. And then the opposite, if it's cold, the cells don't want to lose heat. So the blood vessels are going to vasoconstrict, keeping the heat in the area instead of sweeping it away. Okay, shear stress has to do with causing friction on that endothelial lining. So as blood is flowing through, that actually produces a friction, which over time can wear down the endothelial lining. So this is similar to what I just spoke about earlier. Wearing that down causes a tear in those cells, and they release nitric oxide, and then that's going to cause vasodilation, because with vasoconstriction, remember, a smaller radius, more friction, more resistance. So we want to limit that. We vasodilate, less friction, less resistance, less tearing, less stress on the endothelial lining. Okay. A myogenic response to stretch has to do, myo means the muscle, and it has to do with the smooth muscle cells stretching themselves. Okay, so when there's more blood flow coming in, remember they're going to stretch. It's going to push pressure on the wall of the arteriole. There's a little bit of elastic tissue there too, so they stretch. But that's a signal to the smooth muscle when it stretches to constrict. Okay, so that's going to reduce the blood flow. If there's not enough blood flow going through, the smooth muscle cells won't experience any stretch. So that might be an indication that, again, lower blood flow, we need to increase it. So it'll vasodilate, increasing the blood flow. Okay. This is similar to then what happens if there's a blockage in the arteriole, or what we call the reaction to it is reactive hyperemia, reactive hyperemia. So this is called by something physical, a blockage, or what we call an occlusion. So if that blockage blocks up the blood vessel, that's going to cause less blood flow to the tissues down the way, right? So there'll be less stretch, which we said caused vasodilation. Okay. Actually, let me stop sharing this screen and let me go back to the whiteboard, because I might be able to illustrate that for you a little bit better. So here is a blood vessel, and it is branching into an arteriole, okay, and into the capillary bed right there. Okay, so let's say that blood is flowing along. Oh, there's an occlusion. Blockage or occlusion. Whoops. Gotta spell occlusion correctly. Ah, boy, I'm having a hard time with spelling right now. Occlusion. Alrighty. Finish that. So when the blood flow now is coming here and there's the occlusion right there, that means the blood flow on the other side of the occlusion is going to be less. So I'll indicate that with smaller arrows. So again, these smooth muscle cells, there's no stretch. And we just said, we saw on the other slide, that when there's no stretch, then we get vasodilation. So when this vasodilates, all of a sudden this blood vessel gets wider, right? And if that blood vessel then can get wider, right, then that's going to allow, oh, I should do it wider over here too. There we go. I didn't draw that very well. When that gets wider, that pushes that blockage through. Okay, and it can break up, and now you can get more blood flow going in. So that's reactive hyperemia. Okay. The other thing that happens with that blockage, here's the blockage, here we go downstream, is that the organs are still doing work, or the tissues, organs working. And so now if there's less blood flow, remember when organs are working, there's less O2, there's more CO2, there could be more potassium, right? With less blood flow, it's not sweeping this stuff away. But again, that then it will cause vasodilation. And when it does, pops that occlusion out and then sweeps all those metabolism away, metabolites bringing more oxygen. Okay, so that again we refer to as reactive hyperemia. Okay, and that's what we said causes a buildup of metabolites. So these two things can both be happening, that stretch and then the buildup of the metabolites. But the reason why we've put this under the physical change is because of the blockage. So reactive hyperemia, because of the blockage, can cause less stress and dilate and metabolites, more metabolites. So that's both going to cause dilation. Okay. In active hyperemia, it was just about the activity of the tissue, either increasing or decreasing metabolites or waste products right? So that's active hyperemia. So you want to make sure that you make that distinction between the two. Okay. There's also another auto-regulation to this myogenic response, and it has to do with mean arterial pressure. So when mean arterial pressure decreases, right, less pressure, which says causes a lower blood flow, right? So blood flow decreases. So the response of the body then is going to be dilation. Okay, that response of the body is dilation. And usually this is kind of a short-term effect, right? Now, what happens if your mean arterial pressure increases? Again, that's going to cause blood flow to increase. Higher pressure means more flow. That then will cause constriction. We don't want too much blood flow going to our tissues because those capillaries are really delicate. They're one cell layer thick. So too much pressure, too much flow can actually break them, especially like in organs around your eyes and your kidney. So if mean arterial pressure increases, remember that's the perfusion of the blood to our organs, then the response of those arterioles are going to constrict. Okay, again, this is normally a quick short-term response to make that quick adjustment. Okay, and then the idea is we go back to homeostasis and our map will go back to normal. But if you have some type of disease situation, maybe atherosclerosis, something like that, and that changes your map in the long term, in either of these cases, you can see that this can exacerbate the problem, right? So if the arterioles stay constricted, that increases blood pressure, which is going to continue to increase blood pressure, right? Which will you'll get a positive feedback loop, and that can be bad. Same thing here. If you have chronic low blood pressure, your arterioles are going to stay dilated, which causes low blood pressure, right? And so you can get a positive feedback loop. So again, the autoregulation normally happens as a short-term response, and the body quickly gets back to homeostasis. But if you have some type of disease process going on, then this can exacerbate the problem. Alrighty. So this is just kind of in flowchart form of everything we just talked about, and you can see the negative feedback. And again, in the normal situation, this would produce. So here's at the arteriole, an increase in perfusion pressure map, right? And that's because of an increase in flow. So increase in flow that causes a stretch of the smooth muscle. So the response to stretch is constriction, right? That increases resistance and that decreases flow. And that'll be a negative feedback to put everything back to homeostasis. Okay. So those are all intrinsic controls, right? We do have extrinsic controls of our arterioles. So we can get sympathetic, we do have sympathetic nerves that attach to our arterioles, usually cause it can cause either vasodilation, vasoconstriction, depending on what area of the body, and hormones, the endocrine system. So remember, extrinsically controlled organs are controlled by something outside of the organ, and it's always the nervous system or the endocrine system. So in this case, we looked at the autonomic nervous system. So there can be sympathoadrenal activation, right? That has to do with the sympathetic pathway to the adrenal gland and releases epinephrine or norepinephrine. That can increase your cardiac output, right? We said that can increase your heart rate, increase the stroke force of contraction, right? But it can also change the peripheral resistance, okay? Because if we, during sympathetic, we want to decrease the blood flow to our digestive organs or the viscera that's written there, right? And so that happens because those cells respond, they have alpha adrenergic receptors, so they respond to the norepinephrine being released at the adrenal gland, and that causes vasoconstriction. But to the skeletal muscles, the cholinergic fibers that go to the skeletal muscles release ACH, and that always causes vasoconstriction in that area, okay? Those are muscarinic receptors, so it's causing the smooth muscle to relax and it dilates. Okay, so therefore blood gets shunted away from your digestive organs and your skin toward your muscles, toward your skeletal muscles. So that's how that works. Okay, so this is going to take us now into the capillaries. And the capillaries, again, I put this picture back up here because all those arterioles now are feeding the particular capillary beds. So again, you can see some of them here, but mostly they're microscopic, so you don't see too many. But all of that, I just wanted you to get an idea. So here's an arteriole coming in, and all of these tiny little capillaries are branching off in the hand there, also in the head. That's how widespread the capillaries are, okay? So the thing to remember about capillaries is they're very thin walled. They're one cell layer thick. That's why in the microscope you can see through them. You're looking through one cell layer. A very small radius. They're only wide enough to get a red blood cell through. That's how wide a capillary is. One red blood cell can fit at a time. So red blood can almost go in single file through capillaries. And they have to be thin like that because they are the sites of exchange. Okay, so a real thin cell membrane is how oxygen diffuses out of the red blood cell across the cell membrane of the capillary itself into the interstitial fluid. And then vice versa with CO2. The same with nutrient molecules, glucose and things like that. Okay, so it really minimizes the diffusion distance is what we're talking about. And then the speed of blood flow. Now we're talking about speed, okay, distance over time. It's actually very slow. And we're going to see that's an odd situation, because think about when you have a hose, right, and you have a wide diameter at the end, water doesn't come out very fast. But when you want to increase the speed, you also constrict it. You can have a power hose, right? And that constricts the opening and the water comes out faster. So that's, again, another property of just tubes and fluid moving through them. It also affects velocity. So by definition, blood should flow through capillaries faster, but they don't. And it has to do with what's called not just the cross-sectional area or the diameter of one capillary, but because there are so many all branched off at each other, you can add up the cross-sectional diameters or cross-sectional areas of all of these capillaries. And when you add that up, the sum total is like a giant blood vessel. Okay, let's look at that graphically. Alrighty, so up at the top, what we see here is, look at the top graph. My pointer isn't working as well up there, but there it goes. This is blood flow rate, okay, blood flow rate. And you can see it's in liters per minute, and that's steady at 5. So throughout our entire cardiovascular system at rest, blood flow is the constant. It's about 5 liters a minute. Okay, this chart down here is just showing you stylistically our arteries, our largest arteries, the aorta, we have one, and then that branches into several arteries, which branch into even more arterioles, which branch into capillary beds, which go back into venules, and then our veins, and then the inferior or superior vena cava. So this is showing us, again, at any blood vessel type, the flow is pretty constant over time, okay, at rest, okay? And so we're not looking at vasodilating or constricting right now, just everything is constant, okay? But the bottom graph is showing velocity. So this is millimeters per second, right? We said velocity was distance over time. So this is millimeters per second. What this is telling you, in our largest vessels, we have the fastest speeds. Okay, that's opposite of what we know about tubes and fluid flow. Usually the largest diameters have the slowest speeds, but in our cardiovascular system, it's because of the total cross-sectional area. Again, how wide the vessel, we can sum those up with the other vessels, and that affects the speed of the blood flow. Okay, so we have one aorta, okay, that has a particular diameter. Here's the total cross-sectional area in centimeters square. It's about one of those, so it actually travels at this speed. When we get down to the smaller arteries, there's more of the smaller arteries than the aorta. So if you add up the total cross-sectional area in each one of these, we're going to get more than 4. This is what, maybe 6 to 10, right? Then as we get to the arterioles, there's even more of those. So when you add up the diameters or the cross-sectional area of each one of those, that means we're getting an even wider vessel. Okay. Okay, it increases. Wider vessels means the velocity decreases. By the time we get to the capillaries, there are so many capillaries, hundreds of thousands of them, even more, probably millions. Okay, when you add up the total cross-sectional area, how much lumen there is, right? And all of those, add them all together, that's like having a super wide diameter blood vessel. Okay, that's what this says here. The diameter is the largest compared to all of these. It's better to say total cross-sectional area. So in the largest vessels, fluid flows the slowest. Okay, then the opposite happens with our veins, back to mirror what happens with our arteries. This is adaptive. Think about it. If blood just flew really fast through our capillaries, there wouldn't be time for the diffusion of oxygen and CO2 and the nutrients and the waste products. There would be no time for that. So we need the capillaries to have a slower rate of blood flow, a slower velocity of flow. I should say that correctly. So that diffusion is able to occur, okay? So again, it's total cross-sectional area. How much space is in the lumen of all of these blood vessels? And when you add up all the capillaries, it's like it's the largest diameter or cross-sectional area of a artery, bigger than the aorta. So therefore, fluid flows more slowly. Okay, this is important for you to understand. A mistake a lot of students make, they mix up the word total. We also talked about total peripheral resistance. This is totally different than that. Okay, this is total cross-sectional area. So don't mistake those terms. You have to be strong in your terms in order to understand this well. Okay, because again, when blood gets into the capillary, they're leaky. Okay, things can leak out of them. There's pores, okay? There's exchange surfaces, all things can happen. And it varies, those pores vary from organ to organ. You can also get bulk transport, endocytosis and exocytosis. Okay, so these capillaries are leaky, But again, if the fluid is flowing too fast in there, it won't be enough time for the diffusion to occur right across cell membranes, or to diffuse through the pores, or for endocytosis and exocytosis to occur. All righty, I think that's where, yes, I'm gonna stop this one here, and we will do part 3 of the videos. We'll talk about the veins and bring this, and then we're gonna bring it all back together. So I'll see you in a minute.